Welcome to this one. Mr. Sutton here, bringing you the Pre-Cal Honors Chapter 2, Quiz 2, Review Solutions on Graphs and Applications of Polynomials. To graph a polynomial, whether it's an intercept form like this or any other form, we need four things. We need to know where this thing is touching the x-axis, where, if possible, it's touching the y-axis. We also need to know what it's doing at the ends, the end behavior, and also what it's doing at each of those x-intercepts. So let's start by finding the x-intercepts. We can find that by basically setting this whole thing equal to 0 and solving. So whatever zeroes out each of these factors. So that's going to be -6 for that first factor, and that's actually a double root of -6. And then 3 for the other one. So let's put some dots on the x-axis at -6, which is somewhere back here, and +3 somewhere over on the right side. And this is totally not drawn to scale, but it is just a sketch. Now for the y-intercept, we basically have to plug 0 in for all the x values, because if x is 0, then you're on the y-axis. So we've essentially got 6 squared times -3, if I zero out those x's. And then this is 36 times -3, which is -108. And that's going to be somewhere down here. Next, for the end behavior, we have to see what the degree of this thing is, which is to say when you multiply all the x's together, what's your exponent? We also need to know if it's a positive or negative first term. So basically, just ignoring these constants that go with the x's, we basically have an x squared times an x. That's going to give us our lead term, and that's going to be an x cubed. Now, in general, this is going to be a positive x to an odd power. So if you have a positive x to an odd power, this is going to behave basically like a line with an upward slope in terms of its end behavior. So kind of like the graph of y equals x, kind of like this line right here. This means we're going to be starting below the x-axis and ending above it. Now, just to go over a few hypotheticals, if this had been a negative x to an odd, then you would have had a sloping down line, so starting above, ending below. If this had been a positive x to an even power, this would have looked like an upward opening parabola, starting and ending above. And if this had been a negative x to an even, you would have started below and ended below like a downward going parabola. But this was our situation, so we're starting down here and ending up here. Now, we also need to figure out what we're doing at each root. Now remember, there's 3 things that can happen at your x-intercepts. You could cross straight through, you could bounce, or you could go through but in a flattening fashion. And that's going to depend on the multiplicity, basically the number of roots of that type you have. For example, at 6, this is a rather -6, I should say. This is a double root because it came from a squared parentheses here. So double roots are going to bounce, and single roots, like the 3 that comes from this x minus 3, are going to just cross straight through. Now, if you had a triple root, something that had the third power here, then you would be flattening. So putting it all together, we're going to start below the x-axis, and we are going to bounce at -6, go through our y-intercept here, and now we're going to cross at 3, and you'll notice that we end up above the x-axis, which is where our end behavior said we should end up. Notice that if you start in the correct place and make the correct choice at each of your x-intercepts, you should end up in the right place. And then this end behavior over here is really just kind of double-checking that you are in the right ballpark. To graph a polynomial that is in standard form, like this one, we're going to still need all the information we needed in intercept form. So roots, y-intercepts, we also need end behavior and root behavior. The difference is that we have to do slightly different things with this form to get that information. For example, for roots, we can't get the roots in this format. We need things factored out. We need intercept form to easily find the roots. So our very first step is actually going to be to factor this so that we can get the roots. So taking a look at this specific situation, I always look for common factors before anything else. And I notice these all have at least an x squared. So I'm going to take out an x squared. In fact, since there's a negative for this lead term, I'm going to take out a negative x squared just so that first lead term is positive. So factoring out a negative x squared, this negative x to the 4th becomes positive x squared. And then this 7x cubed, now I've got a negative 7x. And finally, negative 12x squared becomes positive 12. I can factor the stuff inside a little bit more. I need factors of 12 that add up to negative 7. 1 and 12 won't do it, neither does 2 and 6. 3 and 4 works, though, if you have negative 3 and negative 4. So I've got a negative x squared still. I've got an x minus 3 and an x minus 4. Now that I've got intercept form, I can just zero out each of these factors to get my roots. So for this x squared, we see that we have a root of 0. And then for this middle factor, we have x equals 3, and then 4 for this last factor. Putting those on this graph here, we've got 0 at the origin, 3 is somewhere to the right of that, and 4 is somewhere further to the right. So now we know what our graph is going through in terms of the x-axis. It can't go through the x-axis anywhere else. In terms of y-intercepts, you might notice that we have the origin here, which is both an x and a y-intercept. It's on both axes. But you can always double-check x-intercepts. With standard form, you're always looking to see what the constant is at the very end. Now here we have an invisible 0 for a constant, but whatever the constant is, that's going to be your y-intercept in standard form. And you can think about it as if you zero out all the stuff with x's in it, you're just going to be left with that constant at the very end. So our y-intercept is 0, but we already kind of knew that by looking at the graph. Now for the end behavior, we always have to look at the exponent and the sign of the lead term for that. But the lead term is already given to us in standard form. In this case, it's this negative x to the 4th. So that's a negative x to an even power in this case. And we know that this is then going to behave like basically a negative x squared, like an upside down parabola, which means we are going to start below the x-axis and end below the x-axis. And now for the root behavior, taking a look at what we're doing at each of these intercepts here, 0 is a double root because it came from this x squared, so we're bouncing at 0. And then 3 and 4 both came from single power factors, so we're going to cross straight through those. So starting below the x-axis, we bounce at 0, come down here, come back up and cross through 3, then we come down and cross through 4, and we end below the x-axis, which is where our end behavior said we should end up. For this problem, to find a possible equation for a polynomial graph, let's start by figuring out whether the whole thing should be negative or positive. We can do that by looking at the right side end behavior. If the right side end behavior is ending above the x-axis, going up, then the whole function is going to be positive. If this right side end behavior were going down, then we could conclude that we had a negative function. Since we're ending up here, that means we have a positive function. So I'm going to write y equals, and then you can think of there as being kind of an invisible plus sign right here. I don't have to write it, but it's there. Now I also need the factors that I'm going to do for this. It's going to be in intercept form. So I have to look both at where we are crossing and the manner in which we are touching the x-axis, whether we're crossing straight through, bouncing, or flattening. So it's always going to be x minus whatever the root is. So for this first one, we would have x minus negative 9, or just x plus 9. And the exponent that goes on this factor, again, is going to correspond with whether you're crossing, bouncing, or flattening. If you're just crossing straight through, then you've got the first power, that's just a single root, and you don't have to write a little 1 up here, although you could if you wanted to. Now for this next one, we're bouncing at negative 7. So this is going to be x plus 7, all of that to the second power. And then for this last one, we're flattening through 2. So this is going to be x minus 2 raised to the third power, because we have triple roots giving us flattening. And this is a possible equation. To write a specific equation of a polynomial where a point is given, such as this problem where they gave us the point negative 1 comma 4, they told us that point, which is right about here, is on the graph for sure. We're basically going to start by finding a possible equation, only we're going to put a little a out in front of everything just to represent kind of an unknown constant that we're going to have to find to make things really specific. So we also want to figure out in the beginning, should this function be positive or negative? So taking a look at this one, since we're ending above the x-axis, since we're going up as we move to the right, this should be a positive function when all is said and done. So I'm going to write y equals positive a just to kind of start things off. And after that, I'm going to put in all the factors here that we need. Now, if this had been going down as we move to the right, then I would have written y equals negative a. But since it was ending up, we have a positive a here. All right, so for our factors, it looks like we are crossing it, or bouncing at least, at negative 2. So that's going to give me a factor of x plus 2, which is really x minus negative 2. And I'm going to have to square that because we're bouncing. So it behaves like basically behaving like an x squared at that one spot. So x plus 2 squared. And then let's see here. We come back down and cross, it looks like, through x equals 1. And that's just crossing straight through, so that's a single root. So I'm going to write x minus 1, and then basically an invisible first power there. And we're also crossing through x equals 3, so we have an x minus 3 to go at the end. At this point, we still need to find what this a value actually is. So to do that, we're going to plug in the point that they gave us, negative 1 comma 4. So 4 is going in for the y right here. And I'm going to substitute negative 1 for all these x's. So I've got a times, and now I'm going to have negative 1 plus 2 squared, negative 1 minus 1, and negative 1 minus 3. Cleaning things up a little bit on the right side, negative 1 plus 2 is just 1. Squaring that, still 1. So that's just 1a, so that doesn't really change a whole lot. Next we have a negative 2 and a negative 4. Multiplying those gives me a positive 8, so I end up with 8a on the right side. Dividing by 8 to get my a value, I've got 4 over 8, which is really 1/2 if you reduce that. And then as our last step, don't forget to actually plug your a value back into what you wrote in the beginning. So this is going to be y equals 1/2 x plus 2 squared, x minus 1, x minus 3. And that is a specific complete equation. On this problem, we have a manufacturer cutting squares from the corners of a 5 by 13 centimeter piece of sheet metal, folding up the metal to make an open top box, and we want a formula for the volume of said box, the domain of this formula, and the length of the squares and maximum volume for this box. And we're going to have to use a calculator at some point. So here's a visual of this one. Here's our rectangular piece of sheet metal with the squares that are going to be cut out of the sides. And to do anything here, if I want to get it, well, first I need a formula for the volume. So in general, for a box, that's going to be length times width times height. But we want to get everything in terms of one variable to be able to do all these other things they want us to do. So I'm going to let x equal the length of these squares, because that's what we really have the most control over, is how far we cut into this metal to get these squares. So that'll be x. And it turns out that the length of these squares is actually also the height of the box when you fold up the sides. So we've already got the h taken care of. Now we also have to get the L and the W from length times width times height. So the length is going to be this side that you fold up here. In the beginning of the problem, this is 5 centimeters, but we're cutting 2x out of it. So it's actually 5 minus 2x for this side after we fold it up. And by the same token, on this side, we're cutting out 2x from our 13 centimeters, so we can write 13 minus 2x right there. So using my volume formula, length times width times height, I can actually rewrite this with x now as 5 minus 2x times 13 minus 2x times x. And in order to get the domain for this thing, that's talking about the x values that actually are going to give me a realistic answer, like a positive volume. I'm going to start by finding the roots of this if I set it equal to 0. So to zero out the first parentheses, I get 2.5 for x for that. And then the next parentheses, let's see here, divide 13 by 2, that's 6.5. And if I plug in 0 for this last x, that will also zero out my equation. Now the important piece here is that if I plug in 0 for x, that means I have a 0 for the height, so I don't have a box. If I plug in up to 2.5 here, 2.5 is going to take care of this whole side. The squares are going to be so big that this side is going to disappear, and again I will be left without a box. So my domain, I can only plug in x values between 0 and 2.5. Now you might be wondering about this 6.5, but it doesn't really matter for the domain, because after you go over 2.5, you've already used up one of your sides. At this point, now that we've got the domain and a formula, we can go to the calculator and figure out the x value that maximizes this function. So to do that, I'm going to use fmax on my calculator, and here's what the setup is going to look like. I'm going to have fmax of my formula, which I'm going to enter in the y1, just to save myself a little time, with an x that I always write there, and then the two domain numbers. So let me show you this on the calculator. So here I am on my calculator, and you'll notice that I'm already in my y equals, where I've entered the function that I had for my volume, and there's a little x at the end there. I don't want to forget that. So I'm going to quit out of this now, and to get the max, I'm going to do math 7 for fmax, and I need to put the function that I just put in y1 in there. So to do that as a shortcut, I'm going to do alpha trace, and this brings up my y menu. y1 is already selected, so I can press enter, and now that's the function that I actually entered in there. Let me do a comma with an x that I always put in there, because we're finding the x value, and then for my numbers I've got 0, comma, 2.5. And we can close the parentheses, press enter, and we get about 1.11 if we take it to 2 decimals, and that's going to be in centimeters. So that's the length of the squares that gives us the maximum volume. To find the maximum volume itself, because we're not quite done yet, we have to take that number and actually plug it into the volume formula. Now, since I already entered this in y1, I'm going to go to alpha, trace, and there we go. I'm going to pull up y1 again. This time I'm going to open a parentheses, and I'm going to put the answer, I'm going to plug the answer that I just got into there. So quick way to do that is just to do second, and then this little minus here gives me answer, and then close the parentheses, press enter, and that gives us a volume of 33.27 cubic centimeters. For this problem, I am trying to expand this binomial that's being raised to the third power. To do that, I'm going to use Pascal's triangle down to 3 levels to give me a shortcut formula for doing it. So here's level 0. It's always this 1 here. Level 1 is just 1 and 1. And now for all the other levels, we always write a 1 on the side, and we just add 2 numbers to get all these inner numbers. So we've got 1. 1 plus 1 is 2. We've got another 1 there. And for my third level, I've got 1, 3, 3, and 1. These numbers are the coefficients of our AB formula that we're going to write. And it always starts with a to the highest power based off of the power that they have in the problem. So this is going to be 1 a to the third b to the 0, which we don't have to write b to the 0, so just a cubed here, plus 3 a squared b to the 1, which we'll just write as b, plus 3 a to the first b to the second, plus 1, and we'll have a to the 0, which we don't have to write, and b to the third. At this point, the a value in this formula is this 4x from my binomial, and the second thing in my binomial, this positive 3, that's the b value here. So for a cubed, I have 4x quantity cubed, plus now I've got 3 times 4x cubed times 3 for the b value, plus 3 times 4x times 3 squared, plus 3 to the third power. And I just have to simplify each of these a little bit. 4x cubed, well, we have to cube each of these, so that's going to be 64x to the third. Next, we've got, let's see here, 4x squared, that's really 16x squared. 9 times 16 is going to be, let me think here, I think that's 144 with an x squared. Next, we've got 3 times 3 times 3, so that's 27, times a 4 is going to give us 108 with an x next to it. And then finally, 3 cubed, that's the easiest one, that's 27. So there's our final answer. For this problem, we're expanding x minus 8 to the 4th power, so we're going to use Pascal's triangle to 4 levels to get a shortcut formula for doing this. So here's level 0, level 1. Level 2, we've got 1, 2, and 1. Level 3, we've got 1, 3, 3, and 1. And now for level 4, we've got 1, and 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and then we have a 1 at the end there. And this is going to give us the coefficients of our AB formula for a fourth degree expansion here. So we've got 1 a to the fourth b to the 0, which is just a to the fourth, plus 4 a cubed b to the first, plus 6 a squared b squared. Notice as a's exponent goes down, b's exponent goes up. Next we've got 4 a to the first b to the third. And then finally we have 1 a to the 0, which we don't have to write, b to the fourth. Next, for a, I'm going to plug in x. This negative 8 is going to be my b value. So for a to the fourth, we've got x to the fourth. Next, we have 4x cubed times negative 8. And then we have 6x cubed negative 8 squared, 4x negative 8 cubed, and finally we have negative 8 to the fourth power. Okay, going through and simplifying this, that's x to the fourth. Here we have, let's see, 4 times negative 8, that's negative 32 with an x cubed. Next we have 64 times 6, which I'm not really sure. I'm going to go ahead and do that on the calculator. So 6 times 64, giving me 384, and I have an x squared to go with that. Over here we've got, let's see, negative 8 to the third times 4. So this whole thing's going to come out negative, and we basically need 4 times 8 to the third. I don't know what that is either. So let me go to the calculator for that. 4 times 8 exponent 3. That's 2048, so minus 2048. Don't forget the x there. And then finally, I'm going to go to the calculator one last time to get 8 to the fourth, and this is going to come out positive. Negative to an even power is positive, but we need 8 to the fourth. So 8 exponent 4, this is what calculators are for, good old number crunching. 4096. So this is our simplified expanded polynomial.